What is the role of chemical potential in phase transitions? Imagine a busy marketplace where goods flow from one stall to another, always seeking the best deal. In the world of thermodynamics, particles move in a similar way, driven by differences in energy. Chemical potential is like the price tag that tells particles where they want to go. It measures how much energy is needed to add one more particle to a system at constant temperature and pressure. When particles move from one phase to another, like from solid to liquid or liquid to gas, they are responding to differences in chemical potential. Think about melting ice. The chemical potential of ice in the solid form is higher than in the liquid form at the same temperature. Because of this difference, particles tend to leave the solid and enter the liquid. When the chemical potential of both phases becomes equal, the system reaches a state called equilibrium. This is when no net movement of particles occurs, and the phases coexist peacefully. It's like two shops with the same prices, so no one has a reason to switch. Chemical potential also helps us understand why phase changes happen when conditions change. For example, increasing temperature lowers the chemical potential of the liquid phase, making it more likely to turn into vapor. Conversely, increasing pressure can raise the chemical potential of the solid phase, encouraging it to stay solid. When the chemical potentials of two phases match again, the system is at a point called the phase transition. This is the moment when the substance shifts from one form to another, like boiling water turning into steam. In the bigger picture, chemical potential acts as a guide for particles, showing the direction they want to move to reach the most stable state. It's closely linked to the concepts of entropy and spontaneity. When a phase change reduces the overall free energy of the system, it happens spontaneously. The system naturally moves toward a state where the chemical potentials are equal, which means it's in balance. If the chemical potential difference is large, the system is far from equilibrium and will change until the potentials match. Understanding how chemical potential influences phase transitions helps us see why materials change from under certain conditions. It explains why ice melts when heated or why water boils when pressure drops. It also shows how systems tend to settle into stable states, balancing energy and particle distribution. So, chemical potential is like the unseen hand guiding particles through their journey from chaos to order, shaping the very nature of phase changes and the balance of matter in our universe.